There we go.
I think it's, we can start now. It's a pleasure to welcome Andy Manion from USC. Andy will give a series of 2 talks on high representations and content Heegaard Floer homology based on his work with his recent paper with Raphael Rouquier.
Thank you very much. Thanks to the organizers for the invitation. I will be talking about joint work with Raphael Rouquier that just appeared a couple of weeks ago after a long preparation period. So I'm very excited about this and hopefully going to share some of it with you. So the overall organization is going to be, just making sure I can click through here. So I'm going to give 2 talks on this this week and next week on Friday. And the organization is going to be, today I'm going to be talking about a certain algebraic operation, a higher tensor product operation for 2 representations of a particular DG monoidal category. And this is a type of construction that Rouquier has a general theory of that has not yet appeared. But in this specific case, we give the construction here and we relate it to Heegaard Floer homology, specifically cornered Heegaard Floer homology. So that will be discussed in the second of these 2 talks. In the first talk, I'm just going to talk a bit from a diagrammatic pictorial perspective about the tensor product operation that we define in this paper. So the organization is going to be, well, the diagrammatic language I'll use to talk about this tensor product is going to be the usual string calculus for 2 categories. So hopefully that's familiar to some of you. And then in the next talk, there will be different types of diagrammatics, the more bordered Floer strands algebra sorts of diagrammatics, and they will interplay with the ones that we'll talk about in this talk in an interesting way. But I'll start by explaining these string pictures and defining a particular DG monoidal category in terms of these string pictures. And I'll talk about 2 representations of such things and talk about how to define tensor products when we have this particular DG monoidal category having a 2 action on some other DG category. That's going to be in section 2, and we'll try to give some motivation for why you would define things that way in section 3. And then in section 4, it'll be a variant of the construction that's especially important for relating with cornered Floer homology. And this is when I have a 2 action of my DG monoidal category or 2 category acting as bimodules and bimodule maps for some algebra rather than functors and natural transformations for some category. And we can also define a tensor product in that situation. So that will be the final thing I'll talk about in this talk. Hopefully I'll be able to get through this all. I might have to click through some slides at some point. There's a relatively large number, but there's lots of pictures. So let's get started though. Recall, if you're hopefully familiar with this notion, otherwise a 2 category is just something like a category, but instead of just objects and 1 morphisms, you're also going to have 2 morphisms between your 1 morphisms. And to have a 2 morphism from F to G, for instance, then F and G must have the same source and target. I can compose 1 morphisms, F from X to Y and then to Z, and then I could also compose 2 morphisms in sort of 2 ways. There's a horizontal and a vertical composition that's going to be implicit in a lot of what we say, but I mostly want to keep in mind the following 2 examples, and then we'll see another few relevant examples here. First is the 2 category of categories, and I'm not going to be very precise about what I mean by 2 category or precisely how weak or strict the structure must be. But it will be relatively clear everything in this talk is very strict or up to isomorphism. That's the flavor of this paper. Great. So we have a 2 category of categories, functors and natural transformations. You could also consider algebras, bimodules, and bimodule maps. And we're going to be taking things to be k-linear over a field K. And it's going to be of characteristic 2, not really just because we like not writing signs, but somehow it's a non-trivial task to lift some of this stuff from the characteristic 2 case, the characteristic 0 case, especially when the bordered strands algebras come into play. So there it's especially formulated in characteristic 2, and we'll follow that. And just as a, so if you don't like two categories, but you like monoidal categories, then you can just view them as two categories with one object. And that's what all the two categories of this talk will be, except cat and alg. They don't have one object. But the smaller sort of diagrammatic two categories we consider will all be equivalently viewable as monoidal categories. But they might be DG monoidal categories, for instance. Okay. And so there's a convenient notation for drawing if you want, especially it's good for drawing two morphisms in a two category. You also indicate objects and morphisms in this language. So this is the string calculus. And so I drew this picture here. Suppose I have two objects, x and x prime, in a two category. Then along the top of this little blob, I have three one morphisms being composed, f3 prime of f2 prime of f1 prime. And that composition goes from x to x prime. Now the bottom of this blob is f2 of f1. That also goes from x to x prime. And I can draw a picture like this to indicate a two morphism alpha from f2 of f1 to that top composition. Okay, so this is the normal sort of non-string calculus way of viewing things, but I can draw a string calculus way of viewing things as well. Here, rather than having objects as nodes, one morphisms as edges, and two morphisms as cells, it's sort of reversed. So you're going to have objects as your, in this case, two-dimensional regions. The strings are going to correspond to one morphisms, and this whole picture, which sort of has a node in it labeled alpha, that's going to be representing a two morphism. So a little bit, so just with this example in mind, hopefully it's clear enough how this notation works. But just to be a little bit more precise, if I want to represent objects or one morphisms or two morphisms in some two category in a notation like this, then I'm going to have a set of possible labels I can put on regions in the diagram, and those are going to be, the possible labels are going to be objects of the two category. And then I'm going to be able to draw some strings, and they should be labeled too. And which possible labels? Well, they should be the one morphisms in the two category. And if I draw a string with a particular label, well, that one morphism has a source and a target. And to have a valid picture, it had better be the case that the region on the left of that, and I messed that up. I actually want the source on the right and target on the left. Let me, I wonder if I actually don't want to take it out of, well, okay, I can do this. Let's see if this works. You know, I don't want to try writing on this because it's going to take a little bit of time, and I'm sort of got a lot of slides to get through, but I messed it up. So I want the source region on the right of the string and the target region on the left of the string, just like in this picture over here. We had like F1 with its source region X on the right and its target region X1 on the left, okay? So that's how you depict one morphisms, is these strings, and then a two morphism, I could think as a box or a little circle or whatever type of node, labeled by the name of the two morphism. So that's how I could depict a two morphism, is just, in general, I could just draw that sort of picture. Or if there's specific ones I care especially much about, I could give them pictures. I could choose a picture rather than having to draw a box with a label every time. So I could say, for instance, suppose I have a two morphism from a, you know, some blue one morphism to itself, and let's say its name is xi. Well, maybe if this is the one that you're familiar with, maybe you'd prefer to draw that as just a dot rather than a box labeled with xi. That type of shorthand is very common for this calculus. And similarly, if I have, you know, something with it's something from a composition of, you know, some one morphism, some endomorphism of some region, then composed with itself, that will give me these two red strands in the next picture. Then if I have this box that's sort of mapping from two red strands on the bottom to two red strands on the top, maybe I want to give that a more crossing style picture. That's, if you're not familiar with the examples in which one uses these pictures, that's all right. But in general, we'll see some instances where we represent two morphisms with, you know, pictures like this, especially crossings in this talk. Okay, so this is just a way of visualizing and drawing and doing computations with two morphisms in a two category, but you can also use this calculus to define two categories. And typically one is going to define relatively small diagrammatic sorts of things and look at maps of those into larger two categories. So if you want to define a two category with this calculus, you want to specify a set of possible region labels. So that's going to be the objects. You want to specify a set of possible colors for the strings, and for each color, what the source and target region labels should be. And then that will tell you the one morphisms in your two category. And then, again, I guess there's several typos. I tried to proofread this last night. I mean some generating two morphism pictures, not one morphism pictures. So once I have my colors of strings, that's one morphisms. And now I want to pick certain, I want to say, okay, now I know what my objects, my one morphisms are. Now I want to be able to say my two morphisms are generated under both types of composition by certain things, and I'll pick a picture for each one of them. And then I'll impose some pictorial relations that these two morphisms are required to satisfy, and that should specify for me a two category. And let's see an example of this, because this is the example, well, the first example we'll especially care about in this talk. So we're going to define a two category this way. It'll have only one object, so you can view it as a monoidal category if you want. So that means you have only one region label. And we're going to pick only one color of string as well. We're going to view that as a black string pointing up. And if we want a name, that's going to represent a one morphism from the single object to itself. If we want to give that a name, we'll call it E. And then we're also going to say the two morphisms are generated by a single two morphism from E squared to itself. So E squared, a composition of one morphisms in this string language, I write the strings side by side, and the regions have to line up. And well, that's okay here. We have two of these black strings oriented upwards, and then a two morphism from that to itself would be a string picture where at the bottom I see two black strings oriented upwards, at the top I see two black strings oriented upwards, in the middle there's some picture, and we're going to just say it's generated by this one thing for which we'll use the picture of a crossing by convention. Okay, and what relations are we going to impose? We're going to impose that if I do that crossing morphism twice, I get 0. So I can, what I should say is that in this sort of calculus, you always do the following thing. For two morphisms, your horizontal composition is going to be written as horizontal concatenation in the plane, and your vertical composition is going to be written as vertical concatenation in the plane. That's part of this string calculus. And so if I want to say that this tau squares to 0 as an endomorphism of the one morphism E squared, then I would draw that as this double crossing picture and say that's equal to 0. And then there is one more basic relation that I impose, and then the relation ideal is generated by these. And this is a sort of R3 move looking thing that simplifies, a relation like this makes your two category smaller and more natural than it would be otherwise. Okay, and so this would define for you a two category, and you can check a strict two category, in fact. You can check that it's a strict two category. You can also give it a differential, and that will be very important for this talk. You can say D of this. So what would that mean? A DG two category, that would mean your two morphism spaces are chain complexes. And you have all the structure that goes along with that. We're actually not going to talk about gradings in this talk, and it's a little bit suppressed in the version of the paper that we have right now. So I'll say the word DG, but we're going to ignore the G and just focus on the D. And so DG really means differential, and in this talk. So you can make this into a differential category, two category really, by this crossing resolution rule. So this is due to Khovanov in 2010 as part of a categorification of the positive half of UQ of GL11. And the paper is on UQ of GL12, but contained in that is a much simpler case of GL11, positive half, and that's what this is trying to categorify. So this is just an example of a two category if you don't care about categorification. And So then what do we mean by a two representation of this thing? Well, on general terms, if I define one of these two categories diagrammatically, then I can think, instead of being formal about it, I'll just say a two representation of one of these diagrammatically defined two categories is just an interpretation of all of the, the region labels, the string labels, and the two morphism pictures as actually being objects, one morphisms and two morphisms, and some other DG, in this case, two category. So you're sort of representing all of your basic pictorial data as some things, maybe categories, functors, natural transformations, or maybe algebras, bimodule maps. So that's what we mean by a two and that's the case we'll especially care about. We'll care about taking what I'll talk about is, I guess, maybe not the best language, but I'll talk about two representations into C, where C is either cat or alg, these two categories that we talked about before. You could consider more general things, but the tensor product construction, we're going to have some tensor product construction for two representations into C. There's a closely related one for two representations into alg, but they're not the sort of thing that would just generalize for two representations into an arbitrary two category. The operations I'm going to define are going to use essentially that we're, in the first case, looking at two representations into cat. And in the second case, it'll use essentially that we're looking at two representations into alg. So it'll make use of what cat and alg are, not just, so it's not an operation that makes sense for two representations of this U into an arbitrary two category C, okay? So that's something to keep in mind. So that means there's going to be some aspects that are not entirely pictorial here. So let's focus on this first case of two representations into cat. What do you need to specify one of these? Well, you need to interpret all of this data as, if I said a region label, or then, well, a region label, that should mean a category, DG category in this case. I'll take cat to be DG categories, DG functors, and natural transformations, which form chain complexes in this setting. Okay, so what would it mean to have a two representation of the two category on this page into cat? Would mean I have some DG category for the region, okay, the unique region. I have some DG endofunctor of that category, call it E, and that corresponds to the black strand pointing up. And then I would have some natural transformation from E squared, the functor E squared, to itself. And now I could take D of a natural transformation between DG functors. That's a well-defined thing. And you can, well, because your morphism spaces in DG categories have differentials, and you can take, d tau plus tau d, that sort of thing. But, well, that's just saying that cat is really a DG2 category. And so it makes sense to say not just that, I want a natural transformation tau for which these relations hold, but also, in quotes, d of tau equals 1, where that d is the DG2 category structure on cat, right? It's the differential on a space of natural transformations. Okay, so that's what it would mean to have a two representation of this U into cat. And now if we have two of these things, we want to be able to take a tensor product of them. That's the first thing I'm going to try to define, and then I'll give a small bit of motivation and then discuss an algebra analog. But really this is maybe the core construction of this first talk. Okay, and I'll try to give context later, but for now I wanted to get as quickly as possible. I didn't want to get bogged down in the context because it can take a long time. I can kind of digress on that a lot. So I want to get to the construction. So let's suppose we have two of these two representations of U into cat. So V1, E1, tau 1, and V2, E2, tau 2. Okay, and now how am I going to build another thing of these that's a tensor product in sort of the sense of categorified tensor products on Hopf algebras, or sorry, tensor products of representations of Hopf algebras? Well, the first thing I could say is that I could just take the ordinary tensor product of DG categories, V1 tensor V2. Objects are pairs of objects. Morphism spaces are tensor products of chain complexes of morphism spaces. Well, in some sense, I should have two commuting actions of this U on V1 tensor V2, one coming on the first factor, tensor the identity, and the other identity tensor the second factor. And so we're going to use this type of data. We're going to formalize what it means to have two commuting actions of this u, really by defining another DG monoidal category u squared, such that having two commuting actions of u just means having an action of u squared. Okay, and then given that data, given an action of u squared, we're going to build another category with an action of u. That's sort of a diagonal action type of construction, and that's how we're going to get the tensor product. Okay, and we'll see that a little bit more concretely. So the first thing we want to do is the setup. So under what sort of circumstances am I going to be able to do this sort of diagonal action construction, and then they had better be satisfied in the tensor product case. Okay, so to do this, I'll define an elaboration of this u that we did. Okay, so we're going to define another DG2 category or DG monoidal category using this string calculus. It's going to still have just one type of region, but now I'm going to have two colors of strands because I'm supposed to have two commuting actions. Okay, so I'm going to have a red strand and a blue strand, both pointing up. I'll call those E1 and E2. And well, they should each have their tau on the square of each of those, so that I'll draw as a red crossing and a blue crossing, and those are going to satisfy the same relations as before. And the extra thing I'm going to put in is I'm going to enforce commutativity by putting in an isomorphism, let's say sigma, between E2, E1 and E1, E2. So if I want, I can put in sigma and its inverse and then require them to satisfy these relations. And well, the invertibility relations. So those are the first two relations I list here. Just that sigma inverse is really just an inverse to sigma, so that adding this sigma and sigma inverse is like enforcing that. Well, it's like enforcing commutativity of the two actions. If I do the E1 and then the E2 first, that's the same as doing the E2 and then the E1 first via this identification sigma. So that's the first things, and then the second two relations are just more R3 moves that are reasonable. They sort of allow you to do computations in which isotopia is always allowed. So that's very convenient if you can set things up so that these relations hold, and that's okay. We include these relations here, and that is good. And so, well, we should be able to get this. I should be able to get a two representation of u squared into cat, assuming I have the data I started with on the other slide. Okay, v1 e1 tau 1 and v2 e2 tau 2. I should be able to get a two representation of u squared into cat, and I'm going to do it as follows. Well, the region I'm going to take to be this DG category W, and that's which I define to be the tensor product as DG categories of V1 and V2. Okay, and then my two colors of strands, those get represented as endofunctors of W given by this E1 endofunctor of V tensor with the identity on V2, and then the E2 endofunctor of V2 tensored with the identity on V1. And then sigma, well, in this bottom displayed equation, it says what sigma is. Sigma is the natural isomorphism from the first from the left to the right here, from identity tensor E2, tensor E1 tensor identity to the other way around. So it's just this swap map because both of these are just E1 tensor E2. So we have this data. The upshot is that if I have if I'm given two representations of U into cat, then I can build this data, this two action of U squared on the tensor product on V1 tensor V2. Okay, and now from this data, now I'm going to assume that I didn't necessarily come from a tensor product case. Now I'm going to assume I just have a two action of U squared on something into cat. So I have some DG category W for the region. I have functors, endofunctors E1, E2 of W for these two red and blue strands. I have all of the relevant maps and the relevant relations and differential. Okay, so given that data, this is the crucial construction of the talk. We are going to build something that we call delta sigma of W because it's going to have an action of U that's in some sense a diagonal action acting on you know, making use of the action of u squared in some sense. And it's going to, you know, as an action, as a two representation of u, it won't be just a DG category, but it will have this endofunctor E and this natural transformation tau. So we have to build all of this data, okay? And it matters that what I'm trying to build is a DG category and a functor and a natural transformation, rather than some other object, one morphism and two morphism and some other two category. So this is specific to cat somehow, okay? So the first thing I want to do is I'm given this data W and the corresponding data. Now I want to define, first thing is a DG category delta sigma of W. And I'll try to explain a bit why you would take this definition in a second. But the objects of delta sigma of W, just by fiat now, are going to be pairs M comma pi, where I would want to say M is an object of W. But I'll end up wanting to take mapping cones on morphisms. And so I do want to at least take the pre-triangulated closure of W, and then idempotent completion is thrown in because that's a more natural thing to look at. But this M is taken to be an object of the Karoubi envelope of the pre-triangulated closure of W. And then pi is supposed to be, well, some sort of morphism in this closed W, that from E2 of M to E1 of M. Remember, E2 and E1 are taken now to be endofunctors of W, and M is an object of W bar I. Well, E2 and E1 extend endofunctors of W bar I, so that this makes sense in a unique way. And so that's what objects are going to be, certain sort of pairs, but not all such pairs, right? So I want to define this delta sigma of W. I'm saying what the objects are going to be, and it's going to be certain pairs M pi. Well, which ones? To do that, let's draw pictures, okay? So what would such a map pi look like in string calculus? Well, I'm going to assume I have some object M of W bar I, and I'm going to introduce a new string for that. I can sort of view that M as a functor from a trivial category into, well, I don't want to try to be too precise about it, but heuristically, I hope it makes sense that just like I can consider E1, E2, E1, that sort of composition of endofunctors, and I can write those as strands concatenated horizontally. I can also view these things acting as an object by just having a strand for the object at the right. I'll give that a different color. And then this sort of picture, if I have on the bottom E2 M as my two strings, that's supposed to represent E2 of M, on the top E1 of M, and this morphism between them I would represent. In this case, I'm not going to pick any sort of special picture for such a pi. A morphism from E2 of M to E1 of M in W bar I, really, I'm just going to write as this pi box like this, okay? And so then, okay, what I'm trying to say is which M pi are allowed to be objects of delta sigma of W. Well, it's the one such that pi satisfies this relation, okay? So if you have an M, and then I have a pi such that this is going to be natural transformation on the left equals this, well, really it's I wouldn't say a natural transformation, it's a morphism in W bar I on the left equals this morphism on W bar I on the right. Then I have a valid object of this diagonal action construction delta sigma of W, okay? So objects are these pairs M comma pi, and then I guess I should say, yeah, if you have questions, feel free to stop me. I want to try to go fast, but I don't want to be completely.
Okay, and what's the motivation for this relation you wrote on the right? What's the motivation for?
Okay, so that is right. Good question. It's a relatively, if you're going to write down a natural compatibility condition that relates both tau and pi, then this is the first thing that you would come to. If you view it, I mean, if you try to write it as a commutative diagram, it's maybe even clearer that this is the simplest thing that you could write instead of something else that would really express some compatibility between pi and tau, that in some sense they commute, although that, I mean, you have to do pi twice and then a tau. and there needs to be a sigma in between, as opposed to a tau and then 2 pi's. So yeah, I would say I don't necessarily have the best motivation for this, other than that it seems like usually in this stuff, it seems that if you guess the simplest possible way two things can be compatible, these guesses have a tendency to be relatively accurate, and in this case it is the one that we use.
Sure. And then so another question. So you want to clarify the condition that E is a primitive element of a half algebra. You want to clarify the equation delta E is E tensor 1 plus 1 tensor E. And that's why you're looking for such maps from E2 to E1.
Yeah, that's one way to view it. Yes. I will try to motivate this in this next section of motivation, and I'll say it in a slightly different way. I'll say it in terms of HOMs versus internal HOMs, but the idea is the same.
Thank you.
Okay. Okay, so I'm trying to define this DG category delta sigma of W. Its objects are m comma pi such that pi satisfies this. Okay, and now morphisms from m pi to some other m prime pi prime, m prime pi prime, hard to say. Well, those are just going to be certain morphisms from m to m prime, but we're going to require them to be consistent with the pi and pi prime in the right sense. So if I want to draw such a morphism, it would just be a little box on a strand labeled m on the bottom going to m prime on the top. And then I could draw a picture that basically, this picture that I draw also just encodes the most natural. If you were to just guess what's the simplest commutative square I could write down that relates pi, oops, and it should be pi prime on the right side of that diagram rather than pi. Maybe I'll make an edited version of these slides after the notes, and that's it. But it should be pi prime on the right. But regardless, this expresses the simplest commutative diagram that you could ask for that would involve both this F map and the pi prime on the two sides. So that's morphism in delta sigma of W. And so objects are m pi, morphisms are these F satisfying this condition, and then composition identities, that just comes from where the morphisms live, which is this W bar I, this closure of W. So this is, one can check, a DG category. Okay. And the next thing we want is an endofunctor E of this DG category. And so I need to say first on objects how it acts, and this is maybe the most interesting part of the construction. So on objects, I need to say what is E of m pi. That should be some m prime pi prime, and so I just have to say what m prime is and what pi prime is. So m prime, I'm going to take it to be the mapping cone of pi. And we'll see that's especially motivated in terms of if pi is an isomorphism, then that mapping cone will actually be contractible. And we'll see why that's something that we want in just a second. But in general, here's how we'll build this E. This m prime here will be the mapping cone of pi. So I can think of that as E2 of m, direct sum with E1 of m. Those are objects in W bar I, but with a differential from the first one to the second one. Okay, so and that extra component of the differential is given by pi. And this makes sense. This is why I had to take the pre-triangulated closure, because I wanted to be able to say mapping cone of, I can't necessarily say mapping cone of objects, morphism between objects in W, but if I take closure of W, then it makes sense. E2 of m is an object in W bar I, so is E1 of m. Pi is a morphism there. I can take its mapping cone. That's another object of W bar I. Let's call that m prime, okay? And diagrammatically, I'm going to write it as this sort of E2 of m. That would be the E2 strand blue, and then the m strand black. And then the other summand would be like red strand, black strand. And I write the direct sum with the arrow over it to indicate it's a direct sum, but it's really a mapping cone because the differential has this arrow. But if I'm ignoring the differential, then I can just think of it as a direct sum. And that's useful, especially if I want to, if I want to write, say I want to get a map pi prime from E2 of m prime to E1 of m prime. So I want some way of thinking about those, and I can think of those similarly as direct sums with these extra differentials. So if I do E2 of M prime, that just means stick a blue strand to the left of all the pictures in M prime. So that's what I get in this first picture on in this box. And then for E1 of M prime, it would just be stick a red strand to the left of everything. Okay, so a map from E2 of M prime to E1 of M prime, that it will a map in W bar I, that would be, you would think of it as a 2x2 matrix, where each entry, because I'm mapping from something that has essentially a direct sum decomposition as my domain, as two things, to something that has also a two-thing direct sum decomposition as my target. So if I do that, well, if I look at these decompositions, I can specify a morphism by giving a matrix of morphisms. And that's how I'm going to define pi prime. Pi prime is going to be defined to be this following matrix. So let's look at the top left entry. That's going to go from like the left entry in E2 of M to the left entry in E1 of M. Okay. The top right entry of this matrix is going to go from the right entry of E2 of M to the left entry of E1 of M. And the bottom right entry is going to go from the right entry of E2 of M to the right entry of E1 of M. And so you can just define a map like this. Now, what's not clear at all, just by writing this down, is that this M prime comma pi prime is a valid object of delta sigma of W, so that E actually sent M pi to another valid object of delta sigma of W. Okay, but these are the definitions, and we can just assume that for now. On morphisms, well, my morphism, if I look at if I started with the black strand, then that get mapped to like blue black plus red black with the differential. So if I have an endomorphism F on the black strand, which is just a little box labeled F on that black strand, then I can just define it to be, well, red strand, black box, plus blue strand, black box, with, it's mapping between things with the differential. And so that's, okay, so that's, once I know how to define this E on objects, which is really the interesting part, then E on morphisms is just what you'd expect it to be. And so then one can check that defines, well, I'll say that as a theorem in just a second, but this defines a DG functor from this DG category delta sigma W to itself. And then the final thing that I need is an endomorphism tau of this DG functor squared. Okay, so if I have E squared and I apply that to M, E takes M and it does like blue strand M plus red strand M with differential. So if I do that twice, I'll get 4 possible things: blue, 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 red, red, blue, and red, red, with differentials between them. And well, but just like I used a 2x2 matrix before with respect to a 2-term direct sum decomposition on both, input and output, here we have a 4-term direct sum decomposition with differentials. And so I can use this to define this tau with the 4x4 matrix. And it's sort of what you'd expect except for one term, which is required for everything to work out. Some of these things I won't be able to motivate so much as just saying, once you know certain aspects of the construction and you're trying to get it to all close up and be well defined, then other aspects are determined. In particular, the sigma inverse, this strange entry here in this matrix, you might think that tau just acts only on the blue-blue part and on the red-red part, but actually your endomorphism tau of E squared for this diagonal action is going to have this extra term in the matrix too. But it's not going to matter so much what that tau is for this. Let me just state the theorem that says this is well defined. This closes, and this is got a lot of moving parts to it. So this is a relatively detailed proof in our paper, but you can view most of it in diagrammatic terms. And maybe the most interesting part is this fact that E of M pi, well, this M prime pi prime that we defined, we wanted that to be a valid object of delta sigma. And remember what that meant is this equation, that equation right here. Now, if I take and use that 2x2 matrix, okay, for pi, and then I expand out what all of the different entries of that would be. In the end, I will want a 2x2 matrix equation of more complicated diagrammatic expressions. And just for illustration, not just try to like check this is what you get now, but this is what you get. I mean, these equalities, you can check these using the rules that we've set up, and these are the equalities that amount to m prime pi prime being a valid object of delta sigma. So in fact, two of these, it's easy to check. The ones that says equals 0, okay, the two things that are equal to 0, you can see immediately that they're equal to 0 because they each have a double crossing, okay? One of them has a red double crossing, the other one has a blue double crossing, but they each have a monochromatic double crossing. And so you can see clearly that those are 0. The other ones, it takes a little bit, it's not entirely trivial. It's a sort of moderate difficulty, but not overly difficult diagrammatic verification. Okay, so that's the sort of arguments, and you can write these out in terms of chains of equations like they're written in the paper. We also gave this picture of the diagrammatic version, but however we want to think about it, this is well defined. This gives you from, so remember we started with a 2-action of u squared on w, and now we get this new thing, delta sigma of w, that has a 2-action of u. And this is all, you know, 2 actions on categories, on DG categories. Okay, and so we can look at the tensor product case, and we're just gonna have new notation. So if we got our W as being V1 tensor V2, okay, with its E1 and E2 that came from, you know, my tensor product, my original data for taking a tensor product, then, well, then I'll use this tensor product symbol with the extra circle around the tensor product symbol. Okay, so that's the cool symbol that we get to use in this paper. It's the double tensor product symbol. And in terms of categorification, yes, so this is getting back to the question that was raised before. One can show that, and I don't want to get into too much detail about what K0 means here, but if you set things up appropriately, then well, you could use notions like the split growth and decroup, and then this sort of thing will be relatively less technical. But you can get versions of this statement that this double tensor product thing categorifies tensor product as representations of a particular Hopf superalgebra, and it's the one that's categorified by this U thing. It's the positive half. It's the enveloping algebra of the positive half of GL11. That's a Hopf superalgebra. You do need the super signs in order to get things to work, but that's how it works. And you can thus take tensor products of representations, and that will be another representation. And similarly, we just defined an operation to do the same thing for two representations, and we're saying the one that we just defined categorifies the Hopf algebraic one. Now you should really say UQ in here, and you should really talk about gradings and all of that sort of stuff. That's where a sort of work in progress. We're trying to get versions that are especially adapted to that. But right now, what we have on the archive right now is just basically the differential case rather than differential graded. Okay, so then we want to say U instead of UQ. All right, but that's the categorification sort of statement you can make with this. So you can view this as a categorification of the monoidal structure, at least on objects of H mod. It would be really good to be able to tensor, say, like A infinity categorified morphisms, but that's not something I'm going to get into here. That's definitely also a work in progress. But I do want to say a little bit about why you would define specifically this sort of thing. How would you come up with this definition? And well, here's one explanation that you can try to give among several, I guess. And let's suppose I have a Hopf algebra H over K, and then I have left modules V1 and V2. Well, the context of this talk is sort of, you can take V1, tensor over the ground field with V2, and have a sort of diagonal action of H on that, and that's why H mod has a monoidal structure if H is a Hopf algebra. But similarly, instead of looking at tensor products, I could look at morphism spaces, or HOM. So there's sort of two types. If I have these left modules, V1 and V2, there's really sort of two types of morphism spaces that are important to look at. I could look at maps from V1 to V2 that commute with the action of H on both sides. That's this hom sub H of V1, V2. Or I could, very much like with the tensor product, I could be looking at just things that may not commute with the action. So just, well, they're at least linear over the ground field, but no other requirements. But then on that space, hom sub k of v1, v2, one can define an action of h, so that this is really an internal hom in the category of h modules. And fixed points for this action, which in this case just means the kernel of E, that will be this first thing, this hom sub h. Okay, and you have similar things in the tensor product, but somehow it seems most intuitive to me to think in terms of hom, and this is the way Raphael, I think, would say it as well. I sort of got this perspective from him, of course. This is the tensor product stuff is fundamentally, ideas that stemmed from him in the beginning. So in this case, though, if we look at hom instead of tensor product, then it's sort of relatively easy to guess how I should categorify this hom sub h. And then we'll talk about hom sub k in a second. But for this hom sub h, it's relatively clear. Say I have v1 and v2, and they come with e1 tau 1 and e2 tau 2. Okay, so that they're two representations of u on DG categories. Now, how am I going to define hom over u from v1 to v2? That should be like DG functors from v1 to v2 that commute with the action of u on both sides. And what does that mean to commute with the action of u? Well, yeah, what I want is, I sort of have this functor e1 acting on v1 and e2 acting on v2, and I want a functor f such that if I apply f and then act with e2, that's the same as first acting with e1 and then applying f. Heuristically, that's what I want, but this would be an isomorphism of functors, not just inequality of maps. So it's a common phenomenon when categorifying things like this that you don't want to just require there exists an isomorphism. You want to build in an isomorphism to the data, almost to the data of f, so that you're never just looking at a bare f for which there exists an isomorphism. Rather, you are looking at pairs f comma pi, where pi is an isomorphism from e2f to fe1. Okay, so that's what we'll take to be objects of this hom over u from v1 into v2. There'll be these pairs f comma pi, where pi is this, and this already is looking a little bit like what we had in the tensor product case. And this compatibility with tau 1, tau 2 is exactly the sort of picture that I would draw in the other case. It's just the sort of, if I'm going to draw this visually, the hom has a sort of, the E2 comes in on one side and goes out as E1 on the other, but that's really the only difference. In terms of the commutative diagram you would draw, it's basically the same commutative diagram. So it's some compatibility condition with tau 1 and tau 2. But that's what pi must require, similar to that equation we had for pi before. But that's what objects are, but pi must be an isomorphism here, okay? Because we're trying to encode commutativity. And then you could define morphisms between such objects in the natural way, and you would get a DG category hom sub u of v1, v2. But the objects are these pairs f pi. Okay, so now what we want is a version that early categorifies hom k of v1, v2 rather than hom sub u. So we want to somehow relax the idea that we commute with these E1 and E2 functors. We might allow f that don't have any sort of commutativity with these E1 and E2 functors, but what we really want is that we have an action then on this internal hom. This is going to be a 2 action of u, and I want something that's analogous to, like, well, you're a fixed point for that action on the internal hom if and only if you're actually in the original hom over u, okay? Just like in the decategorified picture. So that, and how would I arrange that? Well, here's one way, and this is maybe the crucial piece of the definition, is that I'm going to take the objects of this internal hom from v1 to v2, the early categorified hom over k, I'm going to take them to still be pairs f pi, but I'm just going to laxify the pi. I'm going to not require it's an isomorphism anymore, okay? But it's always going to still be part of the data because I'm going to use it to build the internal action on the internal hom. So I want to be able to take e of one of these f pi's, and I want that to be 0 in some sense, if and only if I really started with an object of my hom over u. So I want it to be 0 if and only if pi is an isomorphism. And okay, I might be a little bit, this is the heuristic part. So by isomorphism, I may mean something weaker like homotopy equivalence. I just want this vague idea that pi is an isomorphism or equivalence or what have you. I'm actually not sure they're right. It's a little bit subtle to come up with the right homotopical versions of these definitions. And so this paper is all at the strict level, but this is just for motivation. So the idea is that if pi is a equivalence in some sense, well, the mapping cone is going to be trivial in some sense. And so that means you're a fixed point. That means E is acting as it's annihilating your f pi. And so that's, if you make the definition like this, that will happen when your f pi was actually an object of this hom over u, where pi was required to be an isomorphism in this case. Okay, so that's modulo important details, but details that we can safely ignore for now. Well, then you can sort of fill in the rest of the definition. Once you have these pieces of it, you want to make everything close, you need to define a pi prime. There's a natural way to do that. It's similarly for tau, and so, okay, so this, what I'm trying to argue for is that this categorified internal hom has enough intuitive pieces of it that then you can recover the rest, and then you can hope that, well, hom and tensor are pretty closely related. Hom of v1, v2 should be like v1 star tensor v2, at least in finite dimensional vector spaces. So you're hoping that a construction of an internal hom is going to be very similar to a construction of a categorified tensor product, and in fact, you can just mirror this. If I understand right, I think this is how Raphael first thought of it in terms of homs first, but I'm not entirely sure. But this is, well, so this is my attempt to motivate, at least in terms of algebra, why you would do this. We'll see more of the topological Heegaard Floer related motivation next time. We'll see that this is the right structure for understanding the gluing formulas in cornered Heegaard Floer homology. But for now, this is the motivation. And in the last 7 minutes or so, I just want to go over the version that will be especially important, okay, which is, it's cleanest maybe to talk about this tensor product operation, you know, when U is acting on a DG category, but how about when U is acting on a DG algebra? That's the one, there's actually a variant of this construction in that case, and that's the one that's most closely related to Heegaard Floer, because Heegaard Floer, as we'll see in a week, naturally gives you two actions of this U on DG algebras by bimodules and bimodule maps. Okay, so E will be a bimodule over DG algebra, A. Tau will be a bimodule endomorphism of E tensor E. Okay, that's what a two representation is. A, E, tau. A is a DG algebra, E is a bimodule, tau is a bimodule map. Okay, and in the, well, I want to be able to take a tensor product of these. Here's one thing I can say. I can just pass from algebras to categories by taking category of modules, DG modules, if you want. And so then if I have like A1, E1, tau 1, and A2, E2, tau 2, I could take these category versions, and then I could take their tensor product, okay? And that's something I could do. Well, here's something related I could do, more related to sort of Deligne tensor product of categories. And this is, well, this tensor product above, this one here, would be based on A1 mod tensor A2 mod bar I. You know, that would be my W, is A1 mod tensor A2 mod. But I could take W instead to be a sort of Deligne tensor product. I could take it to be like A1 tensor A2 parentheses mod. I still have a two action of U squared on that, basically defined as before. I have these two E1 and E2 bimodules. There's a natural swap isomorphism between them. Now I can apply the delta sigma construction to that. Okay, and this is the one I especially want to look at. So the goal for the remaining 5 minutes, which maybe involve a lot of like this sort of talk, but we'll see. But the goal is, oops, okay, come on. There we go. Okay, the goal is to define an algebra level variant of the tensor product construction. So A1 tensor A2 comma E tau, and the property we want to satisfy is that then if I take mod of that, I pass to the category level, then that's the same thing as on the previous line, where I first took the ordinary tensor product of the algebras, but then I took mod and did this delta sigma construction. So that's, and you know, that's the somehow the cleanest way of stating this relationship between the category level. There's other things you can say as well, but this is what I've used the cleanest way. But we want to define this algebra level tensor product, and we're also going to give it a sort of string presentation. Okay, and the important assumption that we're going to make is that, well, we're going to consider two representations, A, E, tau. E is a DG bimodule over A, but we're going to assume it has a left adjoint bimodule. Okay, left adjoint makes sense in any two category, left dual really. Defined with, you know, unit and co-unit maps. That makes sense in any two category. In particular, it makes sense for some bimodule to be adjoint to another one. And if we want to build in that requirement, just like we built in invertibility, we could just make a bigger category where now we have up and down strands. So instead of U, we'll consider this U bar. You have up and down strands. You have your tau still, but now you also have the unit and co-unit of an adjunction with the down strand as the left adjoint and the up strand as the right adjoint. Okay, and now from these etas and epsilons, I can build, for instance, if I want a tau with two down strands, I can build that from the other things. But the relations I need to impose on this are just the usual relations for tau, and then the triangle relations for the adjunction. And they look diagrammatically like this. So this is sort of bait and switch. Instead of defining an operation, algebra level tensor product for two representations of U, it's really going to be for this U bar, just to assume that we have the right adjoints for the construction. Okay, and differential is going to be what you expect, is that these unit and co-unit maps are closed. Okay, so this is U bar, and we're going to start with two representations of U bar into alg. And so we're going to kind of do it like before. We're going to talk about what it means to have two commuting actions of U bar. So that's, in other words, we're going to define a U bar squared. We're going to have that data on A1 tensor A2, and then we're going to define the delta sigma in that case. And this is going to involve a lot of pushing my right arrow button because I have 2 minutes left. Okay, but once we're able to do that, then I get my algebra level tensor product that I want, because then I can just take this in item 2, I have this 2 action of U bar squared on A1 tensor A2, and then item 3 gives me this delta sigma, and that's how I'm going to define this algebra level tensor product. Okay, so let me click through a little bit to, so this is the U bar squared. It's what you think it would be. You just have 2 types of colors, and well, I guess there's one thing that you maybe wouldn't expect, is that there's this, if you put in your U bar, your red U bar and your blue U bar, and a sigma between them, then from there you can build this lambda map, like in this third dot, and you require that that's invertible as well. Okay, so that's and there's versions where you don't require that, but that's what I'll say for now. You can get the data from the tensor product case. Don't want to focus on that too much because it's pretty simple. But so if we have all of this data, I mean, how am I going to define the delta sigma in the algebra situation? Okay, I wonder if I have enough time. Well, let me just say, the idea is that I want to, this thought process item is that maybe the one thing to say in the remaining minute is that if I start, right, I know one thing I can do. I can take B mod, and then I can take delta sigma of that, okay? And I want an object of that to be the same thing as a module over some new algebra, delta sigma of B, okay? Well, so that means I want a pair M pi because that's an object of delta sigma of B mod, I want that to be the same as the data of a module over delta sigma of B. And well, how am I going to do that? What is that pi in that data? Well, I could take, since I have an adjoint, pi from E2 tensor M to E1 tensor M would be dual to something that looks like you have E1 dual tensor E2 acting on M, right? So it almost looks like M is given as a B module, and well, you know, B mod is already idempotent, complete, and pretriangulated, so it's okay. M is just a B module. And now it looks like the extra data pi should be look like not just B acts on M, but also this E1 dual tensor E2 thing. So, you know, so whatever this delta sigma of B DG algebra is, it should contain both B, because B should act on M, and it should also contain E1 dual tensor E2, because E1 dual tensor E2 should also act on M. And so we're going to just define delta sigma B to be a quotient of the tensor algebra of E1 dual tensor E2. And which quotient? Well, the relations we got from pi, we can translate them into the appropriate relations. And I'm out of time, so I don't want to. Okay, I'm back. That's happened sometimes. I don't want to get too much into this, so you define it as some quotient of the tensor algebra based on what relations you had for pi. But okay, this finally, I did want to get to this final dot because this is really how we're going, and hopefully if you're familiar with cornered Floer homology, then finally this formula connects with something you're familiar with here, is that since we assumed lambda to be an isomorphism, this tensor product construction, this tensor algebra construction, you can write it, if I have a tensor of a bunch of E1 dual E2, E1 dual E2. Well, lambda being an isomorphism just means I can rearrange that, take all the E1 duals to the left and E2s to the right, and I get this type of presentation of this algebra. This DG algebra delta sigma of B is a direct sum over all non-negative M of this certain construction, tensor product of over the certain DG Nilk-Coxeter algebra we call HM, of an mth power of the E1 dual bimodule on the one side times mth power of the E2 bimodule on the other side. So this type of formula, this is an equivalent way to define the algebra, the delta sigma B part of this tensor product construction for two representations of U-bar on algebras, and this is what we'll see especially in cornered Floer homology next time. How to define the bimodule E, well, it's sort of like before. And next time what we'll see is, like I said, examples, two representations of U into alg, not cat, but into alg, like we were doing at the end, that come from these strands algebras in bordered Floer homology. And then we'll see how the Douglas-Manolescu gluing formula becomes a statement like A of Z is isomorphic to A of Z1 tensor A of Z2 as DG algebras. And we'll see also, ideally, if time, how to update that sort of formula into that's not just true as algebras, that's true as true representations of U, which allows for the iterative application of this formula to cutting multiple times. So that is what I had today. Sorry for going a little bit over, but I will try to review a little bit next time and talk about the Heegaard Floer side of things.
Thank you. Let's thank Andy for his talk. I guess let's ask Andy some questions.
Hi, Andy. So I understand this construction and why you're using, say, GL11 instead of GL2, because you're categorifying the fact that the coproduct of E is, you know, E tensor 1 minus 1 tensor. Everything you do, it seems.
Well,
is there an inherent importance to this minus sign instead of plus sign? I mean, you're taking cones.
It's there is, but not in what I said. I mean, in what I said, there's no gradings. Yeah, it's these sort of minus sign. Now, I would say like you won't find that in our paper because we don't talk about gradings in our paper. This sort of thing is
no.
quite
There's no gradings in that question. It's just the homological thing.
I was going to ask about the same thing. So somehow you, instead of plus, instead of delta E equal to E tensor 1 plus 1 tensor E, you're sort of using some variation It seems like.
No, it's super. It's super. The
Or
E
maybe
is
it's, maybe it's super. Maybe somewhere you hit the shift. Somewhere you hit the shift.
yeah. It's a plus sign, but super. So that if I commute two odd things, I pick up a minus sign.
Right. So this begs the question of like what difference, like I actually don't know what's out there, but is there an analogy of this for just normal SL2 tensor SL2?
Well, it's in this work in preparation of Raphael. So this is the sort of first instance of these. So he has this in general for Cox-Moody algebras, but apparently it's a very complicated construction in that case that you can't really avoid doing it very A infinity the whole way through. The really nice thing about this version is that sort of from his perspective, miraculously, all of that complexity disappears in this particular case, and you can do it all up to isomorphism at the DG level without any, additional things that would make this paper take even longer to get.
Right, and that's cool.
Can you briefly say what helps you to make it simpler?
Oh, I don't know, because I don't know his, that would be something about, that's sort of a question about his work in progress that, in terms of comparison, I'm familiar with this, but I actually don't know the construction for SL2. I've been sort of, it seems interesting to think about. I don't want to get ahead of him if he's working on writing this up. I don't want to sort of start trying to crowd in on that or anything.
So I have a related question. So you have this co-product when the co-product is a cone. So is it co-associative on the nose, or it's co-associative like after homotopy up to A infinity thing? Like if you do the thing twice, if you do V1 tensor, V2 tensor, V3, do you have any issues there, or it's fine?
It should be actually up to isomorphism, at least. Well, let me think. In the examples I'm thinking of, it's definitely co-associative up to isomorphism, and that's the sort of thing I think that's more or less, yeah. And that's what I'd expect. I don't actually know off the top of my head to be super confident, but that's what I'd expect, is that whereas in nearly any other instance of this type of construction, you wouldn't expect isomorphism, that in this case you sort of miraculously get DG isomorphisms all over the place. But I'm not entirely sure though. So we'll see. I mean, in the strands algebras, it's clear that if you, regardless of whether you glue the bottom two first and then you glue the top on, you glue the top two first and then the bottom two on, the results are just given by the same pictures. And I don't think anything is necessarily special about those cases, but that's the only thing I'm confident saying off the top of my head.